Hello, welcome back to another lecture. This one's going to be about just basic structures and some of the easy work you can do with data. We're going to spend more time in the next lecture about jockeying data sets around, splitting them, rearranging them, recalculating, aggregating, things like that, with a package I find is perhaps emerging as the main way to move data frames around. But before we get to that, I need to give you some background on how R thinks of data, how it structures, organizes different kinds of data, and I want to just let you know that I think the way people deal with data has rapidly evolved in terms of the depth of the data, the quantity of it, the vast arrays of data that are available to you globally now through the internet. You can think about these giant networks that people have of interactive data sets. We're talking about bioinformatics now in the most broad sense, to include ecoinformatics and diversity informatics beyond just simple genomics and proteomics. So we're looking at a much more rapidly expanding and intensely deep levels of data than were ever possible before computing made it easy to generate complex maps, which by the way is a database overlaid on a geographic grid, or to be mining these old archives of paper records that are still being digitized. So there's lots and lots of data coming at you. R turns out to be a really efficient way to deal with large data sets in perhaps in ways that are going beyond what spreadsheets do. I still use spreadsheets a lot. I don't want to say that I don't. It's something that is sort of second nature to people who grew up playing with data before. Another way to do it was databases. Databases tended to be more alphanumeric, words, names, addresses, things like that. And spreadsheets tended to be more quantitative, built on calculations and graphs. So spreadsheets were sort of the default mode for lots of people who dealt with quantitative before. Not entirely. There wasn't that hardcore distinction between them. But I think what we're starting to see now is that some of those former distinctions are becoming more blurry, and you can have a variety of different data in its raw forms, and then it's all being input into something like R as the way to do the calculations on that. So there are these great big databases that exist out there now. There's these programming languages that are all able to talk to R. So that's getting beyond us, it's getting beyond me. But so let's start with some of the basics. We should understand how R thinks about data. There's at least four different main ways that I can understand, and one of which I use most often, and that would be data frames. Data frames are just a simple table, like a tab sheet out of a big spreadsheet, because you can have multiple tabs across the bottom of Excel, and it can keep going and going further and further back. But we're talking about rows and columns, a flat sheet, where it would be matching a spreadsheet tab. That's a data frame. That's the most common way we deal with the data that we'll be working with in this class. I imagine true for most of what you do in your degree work as well. A more simple way to think about those would be vectors, which is just a simple list, one column if you will, in a data frame. And then an array, which is the three-dimensional grid kind of view for a data frame. So if we think about those tabs across the bottom of Excel, if they're all matching up, so for example I have a really simple one, it has only 2 rows and 3 columns, but there's 4 tabs back, then that's like an array. It's a cube, if you will, of the data. Okay. And then there are matrices. Matrices are very efficient ways to deal with complex data sets, but it's different from a data frame in that there are only numbers in the matrices that are then related to each other. Excuse me. There are calculations that are being computed between the rows and the columns. For example, in a transition matrix, where the life stages are represented and the numbers represent the changes from one life stage to another. Alright, so that's different. Even though you might think of it as being arranged in rows and columns, it's a different way of using that grid of numbers than would be true for a data frame. Perhaps pictures will help. This is a simple graphic that might help explain this. All of the items across the top row here are containing homogeneous data, which means that they would include all data of the same kind. For example, let's just say numbers, okay? These would, across the row at the top here, all include only numbers, or only numbers, or only numbers. That means that this is a vector of a variable. Let's say pH, right? Okay, now in this matrix, there might be only numbers because, again, remember I said anything in row I2 is making a transition to another cell, for example, row I2, but now column 3, J3. So we're talking about these matrices as being calculations related to each other, often across a diagonal. And then there are arrays, where are simply those 3D cubes of layers of matrices, okay? The heterogeneous data, on the other hand, can be a data frame that includes a mixture of words and numbers in another column and another kind of words or numbers in another column. For example, species IDs, family, counts of those species, characteristics of the site that you saw there, forested, etc. might be words, soil pH in another column. So you can have lots of different kinds of data in a data frame, which is why I think that's a general category for most of us to work with. The same sort of thing could be true in something called a list, where you have a mixture of different kinds of data, words and numbers, in a list. Otherwise, it's arranged the same as a vector. Okay? Hopefully that makes some sense. And as I have said a couple times, I'm going to talk about data frames primarily going forward here, although there are times when a vector might make sense to talk about as well. Pedro, doing life history data, works with matrices all the time, and so he can talk about those in far more complete terms than I do. You can work with arrays in R. It's set up to do that, but that gets pretty complicated pretty fast. And for most of what we're doing, which is just simply computing statistical models of data, I think a data frame is going to be usually the context in which we're going to be working. So, data frames and vectors being the main things that I can see us playing around with, okay? All right. We should also understand how R treats any sort of information that you put into it. And it treats them as objects. If I were to import a CSV file, so if you don't know, a CSV file is a comma delimited simple text file that you can save, for example, in Excel, a flat sheet. So one of those tabs in Excel could be saved as a CSV file. That's an easy way to put data into R. We'll do that a lot this semester. And also simply .txt files, text files. So let's say I have this file. I want to put that into R. I could use this command structure here, or I could simply use that set of menu drop-down choices in R to import a file, and it would do this for me. What I do then is I name it something, and I am making an object then called my data. My data is assigned to this whole thing that is the CSV data sheet, okay? I could do the same thing if I want to compute a model of some kind, and I'm using some command on variables that might be in my data, x and y for instance, okay? So if I say, whatever, some command of x and y, I want to be able to keep all of those results. For example, if this is a regression, there's a whole table that comes out from a regression. There's a prediction list of variables, on and on. So I want to be able to keep all that in a simple thing called a model. And I can ask later to see the details of that thing called model. Okay? So I should also talk about what this arrow dash thing is all about. That simply means is assigned to represent, is the same as, or something like that. So in this line, we would have to say, to be completely correct, model, quote unquote, the object, is assigned to represent the results and everything that comes from some command of xy. Okay? We don't tend to use model equals in this place here because equals can be used in simple algebraic terms, and to use an equals up here could be confusing in some cases with R, where it's thinking you're computing something algebraic. If I didn't have a bunch of words here, if I just had some other number, for example, it would be thinking I'm computing an algebraic equation. And to help make that more clear, we use a double equals in R to tell it to absolutely treat this like an algebraic equation. Y equals this simple regression kinds of equation here, right? So we'll try to avoid this confusion by using this symbol up here whenever we make an object like my data or a model. Okay, so this little thing up here is something you see in all the textbooks and a lot of what you see online. Some people object to it and wish they could just do an equals, but look, all you're really doing is saving one simple keystroke. So for clarity, I'll try to do the same thing here and use this as assigned as or read as or something like that in our jargon. Okay, so we should also be careful and think about the different kinds of data we're talking about here. You can have quantitative data represented by numbers, and those might be integers, whole numbers, or they might be continuous data with lots of up to an infinite number of decimal places, right? Now, it's important to make that distinction. We'll come back to that later this semester. For example, if we're talking about counts, they can have a different distribution, not necessarily a normal bell curve, than if you're looking at continuous data. So that's an important distinction to retain for later. But what I really want to zero in on here is the difference between quantitative and categorical data. And this is also something you have to try to avoid some confusion on. So for example, if you had an experiment and you called them treatments 1, 2, and 3, well, that could be confusing if you are importing in a column that's called treatments variables that are in that column 1, 2, and 3, right? Because of course those are quantitative, and R would see those and by default think of them as quantitative data, like integers, right? When in fact what you mean is that those are things named or with a category of treatment 1 or treatment 2 or treatment 3 or something, okay? So they're names, not really numbers. Well, we can make this distinction. We can tell R that those should be treated as categories simply by using the command factor. So categorical terms in R are also called factors. And if I was to simply say factor treatments, I'm telling R, don't treat those numbers 1, 2, and 3 in that column treatments as numbers. Treat them as categories. And what I like to do is rename that. I wouldn't like to say treatments is a factor of treatments, because now I've lost the original thing called treatments, and it is only just this confusing bit of multiple names for the same thing. I like to try to maintain a new name for it if I'm going to be giving it a new kind of calculation. So I would maybe call it F treatments or F treats or something like that, just so I can retain what I've been doing all along. It makes more sense to me. You could, I know, for example, Pedro doesn't worry about that too much. You could just say treatments is a factor of treatments, and it would end up the same for R. The problem might be if you later then are trying to remember what you were working with. So there you go. My preference is to rename it and call it F something as a way of reminding myself that, oh, that's right, this is the factor of treatments. Okay? And you can double check to make sure that that worked. You can ask how many levels are there in my new thing called F treats, and it would list them for you. Levels 1, 2, and 3. It puts them in quotes the same way as it would if you had names or any other sort of words there. So now we know that we have categorical factors in there, and we can convert things that look like numbers into those factors. Good? Okay. Hopefully you would have already been doing some calculations in spreadsheets or have messed around with spreadsheets some already. Remember that they're still very useful for doing lots of calculations, but even as a raw data entry place to organize your data to put into something like R. And you would see calculations that you could do in Excel or any spreadsheet like this. And in fact, they are closely matched in R to the same kinds of terms you might use in Excel. So if you said log of some number in Excel, you're going to get the log base E. That's assumed by default by mathematicians. And exponent of that same number would be obviously the reverse. It would be E raised to the X. Okay? And so you specify log base 10 or 10 to the X to get the opposite version of that. The same way you would in Excel. Square root, rounding variables, and you can specify how many digits to round to very conveniently in R. You get an absolute value. There's lots and lots more. These would be kind of related to some of the basic functions you could use in Excel, and there's lots of those options available too. So now let me think about this. If I had a spreadsheet with a bunch of data, and for some reason I wanted to calculate the logarithmic transformation of that data. I can make a new column in Excel, call it log of x, do that command, copy, paste it all the way down, make sure I didn't choose the wrong places, verify I've got all the right calculations in there, then import it into R. Or I could just have the raw data set up in Excel, move that into R, and then just with one line say calculate log of x, and done. And I would have perhaps saved a bunch of steps, and I could then do that really efficiently for really, really large data sets, which again, remember, we're getting used to doing more so these days than in the days when you could do everything in a spreadsheet. So you can imagine how the same kinds of calculations you can do and manage and move around and recalculate in spreadsheets, you can do pretty easily in R, and often with a command or two, and less work on your part if you do it in R. Okay, there are some times when you come up with weird data, and there are ways to know that that occurs in R, or ways to deal with them in R. So what if you had some sort of calculation you're making? Again, in a spreadsheet you're dividing one column by another column, and if you had zeros in your denominator, that would come out as flagged as an infinite in R. You might get an error statement in an Excel file or something, for example. So things that are just impossible are flagged as infinite, or maybe negative infinite. Not a number can happen. You can get something called not a number that pops up in R. And clearly those things would be something you cannot do calculations on. And in fact, you'd probably have removed them in your Excel file. You might also get missing values that could be flagged with, for example, NA. Some people often will enter NA in a cell to indicate that it was not just simply a zero, it's in fact not any number available. You can have those in data sets that are obtained online, or maybe you enter them yourself that way for that purpose. For example, let's say you have a list of numbers. C parentheses just simply says concatenate. We're going to make a list of everything from 0 to 5. So I just did it this way. 0, 1, 2. That means everything between 0 and 2. 0, 1, 2. Obviously we have an NA for 3, 4, 5, right? So everything from 0 to 5 is this vector, which is called x. So if we calculate the mean of x, and if I didn't say na.rm thing right here, I would just simply be trying to calculate the mean of this list of numbers, and I can't calculate that using an NA. But I can say this little command, na.rm equals true. That is this option to remove NAs, true or false. And if I include that in some sort of statement, it says basically calculate the mean of x and remove any of the NAs that might be in the list. So then obviously I'm getting the mean of 0, 1, 2, 4, 5, right? Okay, so that's an easy way for you to skip past data where those NAs are missing, and you can even worry about those kinds of things for infinites and NANs. But I think what you'll find most often is that those are calculations you made an error and you need to fix. The NAs are matters of what do I do with holes in my data. And what will often happen is that you delete that row, for example, or there might be other ways to work with it. Okay, we'll try to talk about those this semester as well. There are some other things you can do with lists of data. For example, in vectors, you can examine the data in R, and it can also be very useful for proofreading to make sure that things are matched up. So you can ask, for example, how long is a vector? You can ask for its length, and it'll tell you how many numbers are in that. That's really nice if, let's say, for example, you need to talk about how big a data set you have, or let's say you want to make sure that you're computing the length of x and the length of y, so you can be sure that the difference between them might match up with the number of NAs that were in there that you excluded, right? So if there were 3 NAs in x and I had the otherwise I had the data in y, then I should have a mismatch of 3, right? So the length of x should be 3 shorter than the length of y after I've removed NAs. See what I'm talking about? You can use this as proofreading. You can calculate the usual things you might be able to do in other spreadsheet type functions. Notice in Excel you'd have to type out average parentheses a list of numbers. Here you just simply type mean, which I think is kind of nice. It's less typing for me. You can calculate the max and the min the same way you would in Excel or any other spreadsheets. Median, ditto, sum, all those kinds of basic calculations are ways that you can work with data the same way as you might in a spreadsheet. Okay. Now there are some very convenient cheat sheets which I think are ways to retain some of these options that I don't necessarily have memorized in my head either. You've already seen this one. I referred to it in the last lab that we played around in. It's a nice one. It's very detailed. There's lots of options available to it. Another one that's available, actually it's a set of cheat sheets in our studio, is pretty cool. There's two of them specifically that I think are good. Other ones are related to moving data in and out of interactive websites and databases, etc. So here's the R Studio cheat sheets that I'm talking about. There's a markdown cheat sheet, which is a way of inserting language and moving it into Word files, etc. There's one with working around with IDEs, so this is a way to move things back and forth between different kinds of apps. And Shiny, which is a whole other programming language I don't know much about. This is one that I think is pretty slick, the data visualization cheat sheet, which is a way to see some quick commands for making graphs using especially ggplot2, and so you can see really quickly how you might use some of these quick commands to make different kinds of plots. I think this is a nice cheat sheet for learning how to do some of the basic graphing that I need to play with. And then there's also a cheat sheet here for data wrangling that I think is also pretty convenient. We're going to play around with this some more coming up in the next lecture. I'm going to especially be using dplyr, which is this package which I mentioned before is kind of becoming a default for how to jockey data around. And notice that almost all the commands here are related to dplyr and how you do things like selecting data, summarizing data, mutating data, things like that. A lot of it has to do with dplyr. So I'm pointing to this sheet right here because this is something I also keep in hand when I'm messing around with data, and we'll be using that in the next lecture. There are other ones. Here's one I found online. Somebody at the University of Alberta cooked up for ways to look up basic commands in our cheat sheets like that for learning some basic calculations. Okay, that's enough for now. Obviously we're going to move into the next lecture into playing with dplyr and manipulating data frames, because that seems to be a pretty common and pretty well received method for working with data. Okay, talk to you next time. Bye.